more into the detail than normal. And we'll most likely be having regular quizzes on Fridays, thereabouts. So. Okay, again, continuing with MO theory, and what's going to seem a little weird is we're jumping into MO theory right now, and then as we move forward for chemical bonding, specifically molecular structure, we'll go back to certain topics from Gen Chem. For example, Vesper, looking at linear, trigonoplanar, tetrahedral, and so forth, geometries. An MO diagram can give you quite a bit of information, but it doesn't give you everything that you need. So we're going to see that molecular orbital theory is going to be incredibly powerful, but in some cases we will have to go and bring in aspects of other theories to really understand what's going on. Now, with MO theory, we're also going to see that this is something that throughout the entire course will kind of creep back into the discussion, because MO theory is not simply related to s and p orbitals. You can apply it to d orbitals. In fact, you can apply it to combinations of s orbitals and d orbitals, or d orbitals and p orbitals, and so forth. So we're going to have a lot of aspects of chemical bonding that if you've had, in Gen Chem orbital hybridization, sp, sp2, and so forth, or in organic chemistry, discussion of aromatic systems, and so forth, you've actually had MO theory, but only half of it. Again, when we talk about bonding and anti-bonding orbitals. So we're going to see that this is going to be, again, a recurring thing. Now, if we're simply talking about the S block elements, so again, we have energy, I've got a 1s orbital, another 1s orbital. If you want, you can write this as like 1sa and 1sb to represent hydrogen A and hydrogen B. So if we have two, in this case I'm not going to draw it out that explicitly. An s orbital is a sphere of positive phase. When they interact constructively, we get our sigma 1s bonding MO. And here again, I'm drawing it schematically rather than drawing out all the molecular orbital configurations, just because it's a lot faster. But if I can add an orbital or set of orbitals in phase, or waves in phase, then I also have to worry about adding them out of phase. So we have sigma star, the anti-bonding orbital, so we have a bonding MO and an anti-bonding MO. And this is how we can rationalize how we cannot form diatomic helium, because we'll have 2 electrons in bonding, 2 in anti-bonding, and that'll be the end of it. But what we're going to also find is that in some cases a molecule of hydrogen will interact with a metal like nickel or cobalt. How can we have a molecule interacting with a metal, right? Well, what we're going to find is these anti-bonding orbitals, they're only anti-bonding with respect to the molecule itself. So we're going to find that even though these are called anti-bonding, they can participate in chemical bonding with another species, which is going to, again, be just one of these things where it'll be far beyond what you're used to in Gen Chem. Obviously, Lewis dot structures are out the window at this point. So these anti-bonding orbitals, many times when you draw a Lewis dot structure, the anti-bonding orbital is empty. So it doesn't interfere with what you'd expect for a chemical bond. Or it just works out that the symmetry of how these fill doesn't affect your answer. But we're going to see in some cases, we have to use MO theory to explain the chemical bonding of our system. And if we look at these two molecules, so if you have diatomic nitrogen and diatomic oxygen, draw their Lewis dot structures. Lewis dot structures, even though they are fundamentally flawed, are usually a very good starting point for most things, especially if it's organic chemistry. But we'll see, even with a small molecule, Lewis dot structures can lie to us. Nitrogen, we predict a triple bond and 2 lone pairs, 1 on each nitrogen. Oxygen, double bond and 2 lone pairs on each, not oxygen, again, 2, 4, 6, 8, 10, right? So each nitrogen brings in 5, so I've used all my electrons. 2, 4, 6, 8, 10, 12. Each oxygen has 6, so I've used all my electrons. And our octet rule is satisfied, okay? Again, don't be like some of the freshmen where you just keep putting dots in here until everything is saturated, right? If you start with 10 electrons, that's where you gotta finish, right? You can't add or subtract them. What about the magnetic properties of these two molecules? Would you predict diamagnetic or paramagnetic?
Diamagnetic.
Here, let's contrast it. Draw this Lewis dot structure. Nitrogen monoxide. Five plus 6 gives me 11 electrons. So I'm going to have an odd number of electrons. So what I like to do, so I have 2, 4, 6, 8, 10, 11. Well, obviously I haven't obeyed the octet rule, but I've put all my electrons in. I'm never going to fully obey the octet rule because I've got an odd number of electrons, but this gives me 11, right? 2, 4, 6, 8, 10, 11. Or I could do this. Put the 1 electron on nitrogen and go from there. Not going to be perfectly obeying the octet rule. We can predict which one of these is favorable based on formal charges, but right now I don't care about that. Is NO diamagnetic or paramagnetic? Paramagnetic. 1 unpaired electron, right? An odd number of electrons is going to be paramagnetic. But when we look at these, all of the electrons are paired. So we predict diamagnetic. But that's our Lewis dot structure. And again, something that starts to raise red flags of when you have, again, an odd number of electrons, and we're so ingrained in the octet rule that it's not quite working, but we'll say it's fine. It's fine. And so we would predict NO to be paramagnetic, and it should have a double bond. Any other type of shenanigans of putting in a triple bond or anything like that, you're going to have octet rule violations, right? So we know that this is where, and here, again, triple bond and double bond. With molecular orbital theory, when we calculate bond order, we actually get a number. So a single bond is 1.0, double bond would be 2.0, triple bond would be 3.0, and so forth. And as we saw, we can have a fractional bond order in some cases, where we can have a half bond and so forth. Now, if we want to apply molecular orbital theory to these molecules, well, there's, I wouldn't call it a problem, but an obstacle. Nitrogen, oxygen have p orbitals, right? Right now, we just have the MO diagram for the s orbital set. So what do we have to do? Well, we have to put the p orbitals together. Now, I'm not going to go through all of the symmetry, just because, again, time. If I have two p orbitals, I can add them together constructively, and that makes a pi bond, right? What's that if I add these two together now?
Pi star.
Pi star. I'm adding them together, but deconstructively. And notice all I did was I changed the phase. So here they're adding in phase. Now they're adding out of phase. So it will still be a pi bond, but it'll be a higher energy. So we're going to have, just like we can have sigma and sigma star, we're going to be able to have pi and pi star. But we have how many p orbitals? I have two in my hand, but we're supposed to have, what, px, py, pz, right? Two of them, and this is kind of weird, certain textbooks define the bonding axis differently. Most textbooks that I've used shows the z-axis as the bonding axis. I don't know why. Z to me should be pointing up, but that's fine. So let's say our bonding axis is Z. So we have two elements. I'll just leave it very generic. Okay, so that's the z-axis. And then we can make this y and x. Switch those. X, y. It doesn't matter. So px and py are going to look like this. So that'll be one pi bond. And that'll be another, right? But what about the pz orbitals? How are they going to interact? Like this. They're going to be on axis, okay? If the p orbitals are doing this, if they're bumping into each other like that, is this a pi bond?
No.
No. A pi bond means that you're off axis. In this case, we're taking two p orbitals, we're putting them on axis, and that actually gives us a sigma bond, which seems very weird because we associate sigma with s. But sigma in this context is really talking about the head-on interaction. I don't have blue, so I'll stick with the black and white. So if this is my p orbital, call that positive phase, I'll have another one, also a positive phase. All right? And the non-shaded would be the out-of-phase orbital. So when they interact, this is actually a sigma interaction because it's head-on. Pi would look like this. All right? So we're gonna get interactions like that on the sides. So that's pi. Okay. So, pi bond, sigma bond. And by the way, it doesn't matter which way you put them. What's this?
It's a sigma star.
Sigma star, right? In other words, I flipped the phases, okay? That's all it is. Now, again, in PChem 2, Professor Führer will do this, except with calculus. So, in other words, in PChem 2, they actually go through all the mathematics. What we're really doing when I show you and say this is a p orbital, Schrodinger did the math back in the 1920s, 1930s. And I take his word for it, that he got it right. So I don't need to reinvent the wheel. We want to use the results. And so with our molecular orbital diagram, what we're going to see, px, py, pz, those three p orbitals are going to split into two types of chemical bonds. We're going to have two that are pi and one that is sigma. Why can't we have all the pi bonds here? You can't have, right? You can't have the electron, you can't have multiple electron density in the same spot, right? In other words, that's one of the things in Gen Chem when you were learning about them. So in this case, what we can have is we can have the bonding and then the anti-bonding combinations, but we're going to see they split to different energies. One of the handouts I gave you has the result. Now, and I'll draw this on the board, but I want to go through it. We have the 2s combination. Well, why do we need that? Right? Well, Aufbau principle. Right? It's not shown on here, but if we're going to P, we would have the 1s combination, then the 2s MO, and then we get to the 2p. The reason we don't care about those is they're full of electrons, right? Because 1s2, 2s2, so these parts of the MO diagram are going to be full of electrons, so they're not going to participate in bonding. But when we get to the P, that's where things are going to get interesting. And one of the things that's actually observed experimentally is the energy of the pi sigma and pi bonds can be variable. When you have elements where Z is less than 7, equal to or less than 7, and that would be nitrogen, right? This is the MO diagram that's observed. The pi is at lower energy, and I'll show you in a second how we can justify that. When we get to oxygen and beyond, then the sigma is at lower energy, and then we go from there. And what's observed is that again, we have pi, sigma, pi star, sigma star, and here sigma, pi star, sigma star, okay? So the pi star and sigma star actually stay the same. This is observed, okay? In other words, one of the things about a molecular orbital diagram is once you start putting these orbitals together, you can do the math and do the symmetry, but how do you know relative energy? And you don't. If you have two possibilities, they're both valid. And in this case, we'll see that some elements go one way, some do the other. This is something that is a topic of research where someone will have a molecule that they make and they can draw a potential MO diagram for it. But to really strengthen their argument of this is a valid MO diagram, you need data. And we'll see, usually that data is magnetic data. This molecule is kind of simplified, B2. So let's say we have diatomic boron. Now, in some cases, when I say we've got a diatomic molecule, like oxygen or nitrogen, that can be observed, no problem. B2 is really an oversimplification because in the solid state, boron actually is B12. It's actually an agglomeration. But you can actually observe B2 in the gas phase and in other ways. So we're going to just assume that we've got a molecule that has two boron atoms. How are we going to make its MO diagram? We've got two choices, right? I'm going to skip filling the S. Does everybody see why I can get away with that? Right? Because when we put the S electrons in, we'd have 2 here, 2 here, so 2 and 2. So the shell is full, the subshell is full, right? So I'd have sigma and sigma star. So you can put them in. So this is 2p, this is 2p. Actually, let me give myself a little bit more space. I want to draw the other possibility right next to it. And on this one, I'm going to go with just in order where it actually says, for boron, I should be using this. So this is pi 2px, pi 2py, and then sigma 2pz, pi star, sigma star. I'm gonna leave off the designations just to save a little bit of space for time. Okay. The other possibility, 1, 2, 3. We have our sigma 2pz, our pi's, pi star, and sigma star. Sorry, 2p, 2p. Now, off to the side, it's always a good idea. What is the electron configuration of boron? Can you do it without looking at your periodic table? No, electron configuration, electrons, right? So we're going to start 1s2, 2s2, 2p1, right? It's in group 13, right? The next element over would be carbon, which would be p2, and so forth. So what does that mean? Well, it means we got 1p electron. We've got these s electrons, but those part of the MO diagram are completely full and aren't going to participate. But you're more than welcome to put them in. It's just a waste of time. Each boron brings 1 p orbital to the party. Whether you show them as both spin up or spin down doesn't matter. So you have 2 electrons. And that's going to be true over here as well. See, I've got the same molecule, but I'm using 2 different MO diagrams, right? The 2 that are in front of you. What happens when I put my 2 electrons into my MO diagram? Where are they going?
1 in each.
Mm-hmm. That is a no-no because Hund's rule. If you have degenerate orbitals, the electrons want to go in with the same spin into different orbitals. Why is that? Are electrons antisocial?
They have a magnetic field, right?
It's a lower energy state, but why?
They're apart because they repulse each other.
Exactly. An electron has a negative charge. Another electron has a negative charge. Negative charges repel, right? But it's that magic of spin that can pair them together. However, if you have 2 degenerate orbitals, if you give the electrons an opportunity to get away from each other, they will take that opportunity. So that's lower energy. That's what's observed. There are some cases where you observe the 2 electrons together. That's actually a higher energy state. So what will happen is that would decay. So this is fine. But what about over here? I take these 2 electrons, and now what am I doing? I'm putting them into the sigma pz, right? This is a kind of a trivial calculation, but let's do it anyway. What is the bond order for each of these MO diagrams? Okay, so bond order, it's 1/2 of the total bonding electrons, which would be 2, minus the total anti-bonding, which would be 0. Well, 2 times 1/2 is 1, call it 1.0. And here it's going to be the same, of course. So both of these MO diagrams are predicting a single bond, and that's what's observed. But what is fundamentally different between what these two electron diagrams are telling me? And what do we call that? Paramagnetic, right? Exactly. If two electrons are paired, it's diamagnetic. If I have one or more unpaired electrons, it's paramagnetic. And what is chemically observed is B2 is paramagnetic. That's what's experimentally observed. That's why this MO diagram is valid and that one is not. With two unpaired electrons. There are magnetic techniques that can measure both if something is paramagnetic and how many unpaired electrons it has. So this is, in other words, if I measure B2 and I find it has 3 unpaired electrons, well, that's going to be a problem because that doesn't make any sense with the theory we have. But what's observed, 2 unpaired electrons, which says this MO diagram doesn't make sense. That can't be correct. So in other words, in case you're wondering of when somebody makes an MO diagram, that's just pure theory. In other words, I can move these orbitals up and down in energy, but when you have experimental results, and if the experimental result says it has to be paramagnetic, well then you need an MO diagram that corresponds to being paramagnetic. In other words, you can't argue all day long of, well, I think this should be a better MO diagram. Look how symmetry, like, in other words, from a symmetry point of view, this looks much prettier, right? And scientists like symmetry, right? In other words, right? But it's wrong. It's wrong, you know? And again, that's where you have to be very careful that there's theory and then there's the observation, and if the two don't sync up, you have an issue. And we're going to see that's going to come back with these molecules that we have on the board. So let's look at nitrogen and oxygen. On a quiz, like the one on Friday, I will give you MO diagrams. The only MO diagram I expect you to know by heart is for the s orbitals, because it's literally just an s and an s bonding and anti-bonding. And actually, let me do nitrogen. I'm leaving off the 2px, 2py, just to save space, but it gives you the same answer. Right? So again, nitrogen, 7 protons, so we're using the same MO diagram as we do for boron. We switch it oxygen, okay? Again, it's measured experimentally. So to make N2, right, which, again, it's very easy to forget what's going on with an MO diagram. We have atoms, we make a molecule. That's the whole purpose of the MO diagram, right? So the thing in the middle, that's the molecule, the molecular orbital diagram. What is our electron configuration for a nitrogen atom? All right, give it a beginning. So it's 1s2, 2s2, 2p, 3, right? So I'm going to have 3 p electrons on either side. 1, 2, 3, 3. You don't have to do it this way, but I think it's a very good habit. Put them in then erase them, and then dump them into the MO diagram. So we got 6 to place into our MO diagram. 1, 2, 3, 4. Well, we filled our pi, our bonding pi, so where do we go? Well, we go sigma, right? Off-bow principle. Nothing that you learned in Gen Chem is different here. In other words, the Pauli exclusion principle, that no 2 electrons can have the same 4 quantum numbers. Hund's rule, all of it is the same, it's just being applied differently. So we put in our 6 electrons, we filled all 3 of our bonding MOs. What's the bond order? It's going to be, exactly, it's going to be 6 minus 0, which is 3. Which, of course, is completely consistent with what we observe in a Lewis dot structure. Is N2 paramagnetic or diamagnetic? Dia, right? Because all the electrons are paired, right? In other words, you need an unpaired electron. Okay? And that corresponds, I just erased it, put it back. And that corresponds to what we would predict with your Lewis dot structure, right? So score 1 for GN Lewis, for work Lewis, that's correct. But now let's go to O2. So we're going to have an oxygen, another oxygen, O2 in the center. 1, 2, 3. 1, 2, 3. 2p, 2p. And now we go to the MO diagram where everything is more symmetrical. And this time, I'm going to put the little dots in. The dots are just to kind of show connectivity. I'll make these darker so it's easier to see. So we have sigma, we have pi star, and then we have sigma star. And in case you're wondering, the answer is yes. You can apply MO theory to d orbitals. So you'd have 5 d orbitals on this side and 5 d orbitals on that side. Notice something before I go in here, something about MO diagrams that I haven't explicitly mentioned. If you bring in 6 atomic orbitals, you generate 6 molecular orbitals. 3 bonding, 3 anti-bonding, right? So you have this symmetry that goes along. In the case of nitrogen, 3 of these anti-bonding orbitals, they're empty. They still exist. They still are there. And the reason we know they're there is the molecule nitrogen can interact with metals, and it's actually interacting through these anti-bonding orbitals. But like I said, that's something we'll fight another day. What is the electron configuration of oxygen?
1s2, 2s2, 2p4.
Yep, exactly. 1s2, 2s2, 2p4. So now we got 4 electrons. We're going to have a total of 8. Again, 1, 2, 3, 4. 1, 2, 3, 4. Some books will draw one side as spin up and the other side as spin down. It doesn't matter because you're going to erase them anyway. So we have 8 electrons. Well, off-bow principle. We build up. 1, 2, 3, 4, 5, 6. Do I shove 2 more down in here? Well, I got 8. Where are the other ones going? They're going here. And the reason why is there's no choice. You filled the bonding. That's the lowest energy. Well, guess what? This is now the lowest unoccupied orbitals. So we go 1 and 2. So 2, 4, 6, 8. Now let's look at bond order. Now our bond order, it's going to be 1/2 of 6 minus 2. 6 minus 2 is 4 times 1/2. So that gives me a bond order of 2.0. A bond order of 2.0 corresponds to a double bond. But what else is this MO diagram telling me?
Paramagnetic.
It's telling me O2 is paramagnetic. And guess what? If you take liquid oxygen and pour it into a magnet, it's attracted to the magnet. Liquid oxygen is paramagnetic. Okay? So this is correct. This is not.
Does that still mean it has a double bond?
Well, see, the double bond is the bond order. The fact that it has these 2 electrons. Now, again, if we take a step backwards, what we have to remember, this is a wave in phase. We could say it's a wave of 6 amplitude. This is a wave out of phase with 1, since I say that, of 2. And when you put them together, it cancels out, right? In other words, so the thing is, if they're both full, the bond order would be 0. If this is partially full, it cancels part of this, and that's how we get a double bond. This should also tell you something else. Going back to nitrogen, we have 3 bonding MOs. So the maximum bond order we can have is a triple bond, right? You can't get a quadruple bond because we don't have enough orbitals. Guess what? In the D configuration, you can actually get what's called a quadruple bond. That's actually been chemically observed because you've got more orbitals. Take that organic chemistry, that your double and triple bond. Again, in organometallic chemistry, like I said, there are observed quadruple bonds and even a little higher. Along with bond order, again, we predict that this should be paramagnetic, and that is exactly what's chemically observed. In my own research lab, when I'm transferring liquid nitrogen, sometimes the liquid nitrogen will cause liquid oxygen to condense from the atmosphere. And when I was observing this, what was kind of funny is I grabbed a magnet and I started moving it around, and I could actually see the liquid oxygen moving because I wanted to test, did I have a nitrogen leak? Or was it the liquid oxygen? And sure enough, it was the liquid oxygen, because liquid oxygen's boiling point is higher than liquid oxygen, so it condenses first. So this basically says there's a huge problem with your Lewis dot structures, right? That you've been drawing for probably since high school. That you got the bond order right, but you got the magnetism wrong. And the reason why is there is no mechanism whatsoever in Lewis dot structures to deal with these anti-bonding orbital set, because that's not how Lewis dot structures were conceived in the first place. It was all very empirical of observation. Schrodinger moved us into this idea of the wave. And just for some historical context, Schrodinger did his work, again, late 1920s into the 1930s. MO theory started basically, I think, late 1950s into the 1960s. So it still took a while for all of these parts and pieces to get put together. Now with computers, you can do all kinds of simulations and so forth, but it really comes down to being able to schematically draw these things out like this. So again, yes?
So were there not any experiments going on or anything?
Oh, yeah.
Where people were like, oh, well, we predict that oxygen is diamagnetic, but we see
Yes,
that it is.
absolutely.
So
That's one of the strengths of, in other words, yes, people, I don't know the exact date, but I guarantee you the observation that liquid oxygen was paramagnetic had been known for quite some time, possibly in, 1850 or something like that, but nobody could explain why. Now with MO theory, now you can explain why. It's similar to the photoelectric effect. The photoelectric effect had been observed for decades, and it wasn't until Einstein in 1905 that he explained it. So again, these type of things happen where you've got an observation and you just kind of gloss over it because it's not convenient. This says it's supposed to be diamagnetic. My observation says it's paramagnetic. Okay, whatever, and then you just move on. And well, obviously that's not really good. But the framework of quantum mechanics wasn't there until basically, for chemical bonding, until essentially the 1930s, and then so forth. But yes, that's a very good point. That a lot of these type of things, there were observations, and the theory didn't fit. And that's something that again will often happen. With NO, we're actually using the same MO diagram as oxygen, diatomic oxygen, but it's slightly distorted. I only drew it a little bit distorted. Typically what is observed, the element that has the highest electronegativity is actually at a slightly lower energy. Now, one of the things I'm doing right now is I'm dramatically simplifying these MO diagrams. In your book, they have a few that are not simplified. And what I mean by that is sometimes you can have what's called orbital mixing, where the S is actually participating a little bit in the bond. And it gets really murky. So we're going to keep it as cut and dry as possible. But just so you know, when you look at some of the MO diagrams in your book, they might have lines going all over the place. And it's because when you take these orbitals and have them mathematically mixed together, you might get 90% of the PZ interacting and then 10% of the S. In other words, we had what's called S and P character. We're not going to do that because that would be way more trouble than it's worth. I could draw on the paper, but I'm gonna rewrite it. So we've got P, and actually let me put this at lower energy. So the only difference here, again, is we're drawing our MO diagram a little bit askew. Okay, so we've got nitrogen and we've got oxygen. And we're only concerned with the P because, again, the S is going to be full. Terrible looking diagram. Okay, so nitrogen has P3, 2P3. So it's going to be 1, 2, 3. Oxygen is 2P4. So how many electrons are we putting into this part of the MO diagram? 7. The S we don't care about, right? So that's that. So we have an odd number of electrons. Seven electrons. 2, 3, 4, 5, 6, 7. Okay? Now, in our Lewis dot structure, we observe, regardless of where I put the electron, that it should be paramagnetic, right? And that's what's observed, one unpaired electron. So right there, that's okay. But what about the bond order? Calculate this bond order. Okay? 1/2, 6 minus 1. Can leave it fractional. A bond order of 2.5. Again, can you have half a bond?
Yes.
The answer is yes, because electrons behave as waves, and we're measuring their relative intensity. In fact, what is observed is the bond properties, the bond distance and the bond energy that's required to break the nitrogen-oxygen bond is more consistent with 2.5 than it is with 2.0. So this is also something that's experimentally, but again, look at your, are you gonna find a way to get 2.5 bonds in this? No, of course not, because again, there's no way to take into account what's going on here. For the majority of what you look at in organic chemistry and gen chem, you're oblivious to what's going on in the anti-bonding orbitals, except when it comes back to bite you. Like in the case of oxygen, you think it's going to be diamagnetic with a double bond, but it's paramagnetic with a double bond. And there's, you're not gonna try and do that, are you? Right? Or you just basically just throw 2 electrons away, or just throw. In other words, it doesn't make any sense until you look at the MO diagram. So again, this is what's going to be absolutely critical going forward. Is everybody okay with that? With NO being a bond order of 2.0? When you have an odd number of electrons, it's going to be paramagnetic. Okay? But if you have an even number of electrons, like in the case of oxygen, it still can be paramagnetic. So you have to be careful about it. You can't just make an odd even rule and just say, oh, well, no, it doesn't work that way. What about molecules, relatively small molecules, like HF, where now we don't even have the right set of orbitals? Fluorine has 1s1, 1s2, and it has the 1s, 2s, and 2p orbital set, but hydrogen obviously does not. But what we're going to find is that's not a problem. In MO theory, there's no problem with mixing 2 different types of orbitals. Do it over here. If this is my bonding axis, the z-axis, if I have an s orbital for hydrogen, so this is my hydrogen, and over here I've got my fluorine. This would be the pz orbital. Look what type of interaction I have. I have the positive lobe of the pz pointing at the positive lobe of the s orbital, and this interaction is actually going to be sigma. Does that make sense? All right. I don't have a ball for the s. Again, this is the s. It would be doing that, right? Because they're both on the z-axis, right? So even though they're 2 types of orbitals, 2 different, in other words, s and p, they can still interact. What if I do this? Exactly, I'm making sigma star. Notice in this MO diagram, 2px, 2py are non-bonding. And the reason why is hydrogen only has the 1 orbital to interact with, right? So these orbitals are still here, but they're still as atomic orbitals. So I'll redraw that MO diagram. So we have hydrogen, we have fluorine. Hydrogen has its 1s. Fluorine, we've got our 2p. And again, if we want, the 2s for fluorine is here, but it's at much lower energy. And again, based on this argument that I'm on the z-axis, this sigma interaction is the 1s and the 2pz orbital interacting. The sigma star, 1s, 2pz, and then 2px, 2py don't change in energy, right? In other words, they're basically unchanged by this. So now we need to put our electrons in. Well, obviously hydrogen is 1s1, 1s2, 2s2, 2p.
7. Is it 7? I thought it was 7. Fluorine is 7.
Yeah.
5.
Are we both
Yeah,
wrong?
five.
Is that
It's fine.
embarrassing? Oh my gosh.
1, 2, 3, 4, 5, 6. 6 gets us to neon, right?
Wait, does it have 7 available? Oh my gosh, I get a 7 available electrons.
And I would definitely say, as practice, get used to thinking of electron configurations without having to stare at the periodic table. You'll find that you can pick them up pretty quick. So, 1 electron here. Now, if we really want to, so there are the 2s. Well, they're not doing anything. Then we have 5 here. So we're going to have 6 total. One, 2. But where do the next 4 go? Aufbau principle says we build up. So they go here into the non-bonding. They're not going to jump up to sigma star because that's a higher energy, right? So we've got 4 more. 1, 2, 3, 4. When we calculate bond order, it's 1/2 of bonding minus anti-bonding. That's empty. So that's going to be a 0. So that's going to give me a bond order of 1.0. Does everybody see why these are not part of the bond order? Because these are literally non-bonding, right? If you drew a Lewis dot structure, real quick, one, 2, 3 lone pairs, right? 1, 2, 3 lone pairs, right? So in other words, this is actually consistent with your Lewis structure. So we can apply MO theory to everything. Now, if you notice, I'm picking examples where we just have 2 atoms. Can you have molecular orbital theory with 3 or more atoms? Not in this course. In other words, the answer is yes. When you get to polyatomic molecular orbital theory, you start to have to bring in aspects of symmetry to group the atoms together, and it gets a lot more complicated. So for us, we're going to focus on these type of MO diagrams where we've got just 2 atoms on either side. But this is something that when you hear the term aromatic in your organic chemistry, imagine making an MO diagram of 6 carbons in a ring, and that's what this would be. So, but we're not doing that. So.